All right. So the topic of today's session will be on oscillators. We'll try to look at certain points which are apt with respect to oscillators. Okay, maybe then we'll try to discuss about its core operation. So what do we mean by an oscillator? The definition states that it's an electronic circuit that is capable of producing a periodic, okay, so this word is extremely important, a periodic oscillating electronic signal. Okay, now a periodic signal can be a sine wave or it can also be a square wave. Okay, but the most important point is with respect to time it is periodic. Okay, then oscillator is based on positive feedback. Okay, so please understand, it's not based on negative feedback, it is based on positive feedback. Okay, then oscillators convert direct current from a power supply to an alternating current AC signal. Okay, so here we have an important point which is to be discussed at a later point of time. So what does this particular statement say? It says that suppose if you are giving a DC signal here, and if this particular, okay, let me just designate it as symbol O. Okay, so O stands for oscillator, right? O stands for oscillator. So this particular oscillator provides some oscillations. It could be square pulsed oscillations or it could be sinusoidal oscillations. Okay, so this particular oscillator makes use of a DC signal, okay, and in turn produces periodic oscillations. Okay, where do we use these particular oscillators? We use them in clock generators, we use them in the calculators, and we also use them in many of the computer applications. Okay, you can just browse it through Google and you will find that most of the digital watches, most of the digital clock generators, most of the digital calculators employ sophisticated oscillators within them. Okay, then oscillators are often characterized by the frequency of their output signal. Okay, so what do you mean by that? How can we classify, how can we characterize the various oscillators? We can characterize them based on the frequency of their output signal. Okay, which means the oscillations range from the lowest to the highest frequencies, lowest to the highest frequencies. So whenever we say lowest, it could be just in hertz or it could be in kilohertz, whereas highest it is usually in megahertz, and in some cases there are oscillators which can produce oscillations which are in gigahertz range also. Okay, and you know that 1 giga is 10 raised to 9 hertz, right? Okay, so the point is we have a wide range of frequencies that a particular oscillator can generate. Then we can also differentiate the electronic oscillators in two types mainly. The first one being linear or harmonic oscillator, and the second one which is a non-linear or a relaxation oscillator. Well, conceptually a linear or a harmonic oscillator is simple. Non-linear relaxation oscillator is slightly complicated because the oscillations itself are non-linear. Okay, so for your syllabus, we'll try to focus on the linear or the harmonic oscillator mainly. Okay, maybe in your next semester, once you take up the course on linear integrated circuits, you'll be learning more about non-linear and relaxation oscillators. Okay, fine. Now we'll try to understand oscillations. Okay, first of all, oscillations. Okay, pictorially, how do we represent? We'll try to consider the block diagram of an oscillator. Okay, so let it be a oscillator. Within an oscillator, there is always a amplifier. Okay, an amplifier, and you also have a feedback network. Okay, and in the previous slide itself, there was a statement which said that oscillators are based on positive feedback. Okay, so we'll have to stick to that point. So let me just write it as positive feedback network. Now the point is, for an amplifier, especially with respect to DC biasing and all, we had seen that it needs a DC, right? Okay, a DC signal is must. Okay, fine. And to the amplifier we'll be providing the feedback, and the amplifier also produces an output signal, and a portion of the output signal will be taken and fed back through the feedback network. Okay, so that's in plain terms a simplistic way of representing a oscillator. Now we'll assume that this particular thing produces an output V0. Okay, and this V0 should be in the form of oscillations. It should be in the form of oscillations. Okay, and most importantly, since we are focusing on a linear oscillator, it should be periodic oscillations. Okay, so what does that mean? Periodic oscillations, a sine wave with the same amplitude and with the same frequencies throughout is considered to be a periodic signal. Okay, which gives periodic oscillations continuously with respect to time. Similarly, a square pulse with a constant amplitude and a constant frequency can also be called as the one which gives periodic oscillations. Okay, sometimes it could also be a triangular waveform. All these things, they come under periodic oscillations, but most of the times we focus on either the sinusoidal one or the square pulse oscillator. Okay, now one point to be understood here is what has happened to the input signal. Okay, do we really have the input signal here? See, one common sense, okay, is that you always need an input signal to get an output signal. Okay, so input signal Vi, or it could be Vs, right? Okay, Vi or Vs is must if you want an output signal. But if you just go through literature, it also says that an oscillator is a circuit which produces output without any input. Okay, so this is a bit strange. I just write no input signal for oscillator, right? Well, this particular statement is quite strange but true. Okay, now how do we justify it that without any input signal we get output, and that too a perfect periodic oscillatory output? Okay, let us try to understand first the concept of before that, there is also something called as Barkhausen's criteria, which is responsible for the generation of these particular oscillatory signals. Okay, so it is called as let me just write it. Let me select a different color.
Excuse me, sir.
Yes. Yes.
Sir, some of them are still trying to join.
Just a second. All right. So let us just continue further. That Now, what is actually responsible? So what is responsible for such oscillations? Okay, or to be specific, what is that particular condition, the mathematical condition which is responsible for the oscillations to be produced? Okay, so that thing is called as, so that mathematical condition is being called as Barkhausen's criteria. Okay, so I suppose you must have studied about it in your basic electronics itself, wherein you had a brief discussion about the transistor based circuits. Okay, all right. So this criteria is mainly responsible for the generation of the oscillations. Okay, now for this particular amplifier and a feedback based circuit, what is the general equation for gain with feedback? Okay, how do we represent? Well, the gain with feedback can be expressed as AF equal to, where AF is the gain with feedback, is A divided by 1 minus or plus beta into A. Okay, it can be A into beta or beta into A, where simple A is the open loop gain. Sorry, it is just the gain without feedback. Beta into A is called as open loop gain. Okay, and AF is called as closed loop gain. Okay, so now everything depends upon the value of this particular open loop gain. Okay, and the value of this open loop gain was nicely mentioned by a scientist called as Barkhausen, a long way back. And he just mentioned two very simple conditions which ensure that any oscillator circuit can produce perfect periodic oscillations only when these two conditions are met. So let us just focus on those two conditions. The first condition, it states that the overall phase shift of the entire circuit, okay, overall phase shift of the oscillator circuit must be either 0 degrees or 360 degrees. Okay, so that's the first important point related to Barkhausen's criteria. Then the second important point is regarding the open loop gain. Okay, the magnitude of open loop gain. Okay, so this must be ensured that beta into A must be equal to 1. Okay, so if these two conditions are met, then any oscillator circuit can produce oscillations. Okay, fine. So with this, let us try to move forward and try to look at the actual block diagram of a particular oscillator circuit. Okay, before that, let us just go through the Barkhausen's stability criterion points again. So what does it state? It states that when an oscillator oscillates with a steady state signals, then the total phase shift around the loop from input to output and back to the input is an integral multiple of 360 degrees, and the loop gain is equal to 1. Okay, so the meaning of this particular statement is nothing but that the overall phase shift should be either 0 degrees or 360, and the open loop gain beta into A must be equal to 1 for sustained oscillations. Okay, steady state signals or sustained oscillations. Then Some more important points about these things are here. The Barkhausen's stability criterion is a mathematical condition. Okay, we'll have to understand that, which is used to determine when a linear electronic circuit will oscillate. Okay, so we just discussed about these points. Further, where in particular this criterion is useful? It is widely used in the design of electronic oscillators and also in the design of general negative feedback circuits also. Okay, very interesting. I just mentioned that almost all the oscillators are based on positive feedback. Yes, oscillators use Barkhausen's stability criteria. Yes, however, this particular stability criteria is also used in the design of negative feedback circuits, where it is important to prevent them from oscillating. Okay, so please understand, negative feedback amplifiers, they are not supposed to oscillate. If they oscillate, then their core use gets failed. Okay, oscillations must happen only in positive feedback based amplifiers. Okay, all right. Further, the positive feedback that results in a feedback amplifier having a closed loop gain AF. Okay, I just mentioned about this point a little while ago. It should be greater than 1. Oh, so there is something different point here, right? Greater than 1. I just mentioned that it has to be equal to 1. Okay, but now the statement says greater than 1. Okay, let's try to understand its implication. And satisfies the phase conditions will result in operation as an oscillator circuit. Okay, so what does the block diagram represent? Well, in the block diagram we have two sub blocks. The first one is amplifier. Okay, so we are comfortable with this particular block diagram. So that's an amplifier. So initially you have an input Vi. So this particular input Vi is amplified by the amplifier, so that the output V0 appears, which is nothing but gain multiplied by the input signal, and a portion of output or entirely is fed to the feedback network. So beta represents the feedback factor. Okay, so that's the feedback network. Now the feedback network produces a feedback voltage Vf, which is equal to beta multiplied by A into input signal, right? Now for an oscillator, the feedback should be positive. So let us just cross verify the polarities of the feedback voltage with that of the input voltage. Okay, so here it is plus minus, here also it is plus minus. That means both of them are in phase. So I'll just write they are in phase. So in phase applies positive feedback. Okay, fine. Now there is some sort of a switch present here. Okay, so what is the use of a switch? If the switch is open, then it allows some signal to flow through it. Okay, if it is closed, okay, then no additional source can be added up, okay, to it. So that's the purpose of a switch. But why is this particular switch being used here? Okay, are we trying to block any signal? Are we trying to block any input signal? See, this block diagram says that there is input signal Vi here. Okay, but in one of my previous slides I just mentioned that no input signal for an oscillator. So there is a ambiguity here or a confusion about the input signal. Should we use an input signal or should we not use an input signal for an oscillator? So let's try to clear that point. Okay, so what does this particular diagram state? Let's just go back to this particular slide, okay, so that I have some space here so that I can explain the things. Let me consider an amplifier and a feedback network beta. Okay, so initially let there be a very small input signal, very small input signal. Okay, now this input signal is often noise signal. Okay, please understand, I am not applying any real input signal here. Okay, it is just a noise signal which is inherent everywhere, which cannot be avoided. So I am considering that noise signal as the input signal Vi and giving it to the amplifier. Now this amplifier just amplifies it and I'll be getting a output voltage V0. Okay, so now I'll just take a portion of the output signal depending upon the requirement and then just feed it to the feedback network, and the output of the feedback network provides me a voltage Vf. Okay, now I'll just take it and then give it back to the amplifier. Okay, and I'll just discard this original noise signal which represented Vi. Okay, so what has happened now? There is one closed loop. Okay, after one stage, what has happened? There was a original small noise signal present which we considered to be input, and that particular signal got amplified. Okay, and it became output signal, and we just took that output signal, gave it to the feedback network, and now this feedback voltage we are considering and then giving it to the amplifier. So now our Vf becomes Vi. Okay, so in doing this, what has happened to beta into A, which is called as loop gain, open loop gain. Okay, so this beta into A is actually greater than 1 now. Okay, it is not equal to 1. Now since beta into A is greater than 1, let me just go to the second stage of the loop. Okay, now what has happened? I have got some input signal, and this input signal which is obtained from the feedback voltage has further got amplified. Okay, so in the second stage I will be getting a still more amplified signal. Okay, now again I will be taking this and then giving it to the feedback network, and through it again I'll give it as input to the amplifier. Okay, provided beta into A is still greater than 1. Okay, so this sequence goes on continuing till a particular stage. I am saying the voltage further increases. Okay, so what has happened? After each and every stage or loop of the feedback, the output voltage, the amplitude of the output voltage is continuously going on increasing. At the same time, that is because beta into A is greater than 1. Okay, and this feature will continue for some time, and it will stop when beta into A automatically adjusts itself equal to 1 after some point of time. Okay, so this is the speciality of the feedback network. It ensures that after some stages automatically the open loop gain, which was initially beta into A greater than 1, got adjusted to beta into A, which is exactly equal to 1. So when this condition satisfies, the amplitude of the oscillations now become constant, with constant amplitude and constant frequency. Okay, so now just observe. Okay, initially the gain was increasing. Okay, the amplitude was constantly increasing after each and every successive stages, but after some time beta into A got itself adjusted to 1, so that we are getting constant sustained oscillations. Okay, so when this happens, we say that the circuit is perfectly behaving as an oscillator. Okay, so can you identify the significance of input voltage here? See, whenever I say input voltage, the original input was a noise signal. Okay, we are not explicitly taking any input signal. Okay, it is purely a noise signal which got amplified, and then after successive loops of feedback, that particular noise signal itself appeared, or it became a oscillatory signal. Okay, so do we have any input signal here? No, we are not using any explicit input signal. After the first stage, the feedback voltage itself became the input signal, right? So practically speaking, we say that input is present only at the initial stage. Okay, however, for later stages, Vf, which is the feedback voltage, itself acts as input Vi. So without any input, the system oscillates. Okay, so that is the beauty of an oscillator, and it just oscillates continuously unless and until this simple Barkhausen's criteria is satisfied. Okay, we just discussed about only one criteria. Simultaneously, one more criteria, which is about the phase shift. Okay, the phase shift should also be 360 degrees. If any of the criteria do not satisfy, then we will not be obtaining sustained oscillations. Okay, fine. So that was the meaning. Now I hope you can understand the significance of this particular diagram. Okay, just focus. This is the initial noise voltage, and initially beta into A will be greater than 1. Okay, just as we discussed previously. So unless and until this condition is there, the oscillations go on increasing slowly, and after some time, once the steady state is reached, we will be getting sustained oscillations, okay, which are of constant amplitude and constant frequency, in this way. Okay, and these signals will appear when the condition beta into A is exactly equal to 1. Okay, fine. Now how many types of oscillations do we get? Okay, well, practically speaking, we will be getting 3 types of oscillations depending upon the Barkhausen's criteria. So we will assume that the first criteria is satisfied, which is regarding the phase shift. 0 degrees or 360 degrees is met. Okay, then what about beta into A? Okay, now if beta into A is exactly equal to 1, then we will be getting sustained oscillations. Okay, sustained oscillations means, let me just represent it with respect to the time axis and the amplitude axis. Okay, by the way, sustained oscillations have constant amplitude and constant frequency. Okay, so a perfect sine wave represents sustained oscillations, the same frequency. Okay, the period will be same. Now what if beta into A is greater than 1? Okay, if it is greater than 1, then as discussed, the oscillations will be there, but they will increase constantly with respect to time. Okay, so that is, initially the oscillations will be small, and then they just go on increasing, go on increasing. go on increasing. So that if I just take the envelope, it appears as if they are exponentially increasing. Okay, exponentially in the sense, it will be like this. Okay, so they are exponentially increasing. Now, talking about stability point of view, is this particular oscillation recommended for circuits or not? Yes, I am asking the question to you, students. Okay, do we prefer the first type of oscillations or the second type of oscillations? Okay, what I'll try to do is I'll also draw the third type of oscillations, which are the damped ones. Okay, the damped oscillations, for them beta into A must be lesser than 1. Okay, so if that condition is there, then the oscillations will be exponentially decaying. Okay, damped means decaying oscillations. So initially we will be having a very high amplitude oscillations, and as time progresses the amplitude exponentially decreases. Amplitude exponentially decreases, right? Now in terms of stability, the second one, okay, the gain is increasing, the gain is exponentially increasing. So that means in terms of stability, as the gain increases, stability, the stability decreases. Okay, so if the stability decreases, then it is bad for our circuit, right? So we usually do not prefer such kind of oscillations. Okay, except very few practical circuits wherein there is a need for exponentially or growing oscillations. Then what about the damped oscillations? So here the gain is reducing. So what does that mean? Theoretically it means that the stability appears to be increasing. Okay, but what if the gain has become 0 here? Okay, so if the gain is 0, then what is the use of the stability? Okay, no use of this particular parameter at all. Right? So such type of circuits are also not preferred. So in oscillator circuits we usually prefer the sustained oscillations. Okay, so sustained oscillations have a constant gain, and their stability is also excellent. Okay, so these three oscillations will be usually observed in the case of any oscillator circuits. Okay, wherein we usually prefer the first one, which gives us sustained oscillations. Okay, so I hope these things are clear to you, students, right? So what will we do in the next class is we'll try to focus on some of the practical oscillator circuits that are used in day-to-day applications. Okay, so just to summarize, today we try to understand the concept of a oscillator circuit, what type of feedback it is based upon, and what are the mathematical conditions for any oscillator to be satisfied so that it can produce expected oscillations. Okay, so it is purely based on the Barkhauson's stability criteria. If the stability criteria meets, then we'll be getting oscillations. And there are three types of oscillations: sustained, exponentially growing or increasing oscillations, and then exponentially decaying or damped oscillations. Okay, fine. So any doubts, students, you can ask me. I think we'll stop here, and then we'll continue with the practical oscillator circuits in our next class.